Thank you very much for all of you who came to my talk, who were asked to came by myself as well. Thank you for responding. And like that you sacrifice this perfect lunch in this conference from my talk. So, my name is Signant. I work for Cloudflare. Who here knows about Cloudflare? What we do? Who doesn't know Cloudflare? Okay, so yeah, I'll not stop describing what we do. So, but personally for myself, I do Linux at Cloudflare, so I'm responsible for the operating system we run in production. I really like system security and performance, and enjoy low-level programming. So, Linux kernel, drivers, bootloaders, and other stuff written in unsafe programming languages. Okay. So today we're going to talk about TPMs and Linux kernel. So just a small recap. So what is a TPM? So we get on the same page. So TPM is just a small and cheap security chip present in most modern laptops and servers alike. So it's basically everywhere. All your devices, like desktop devices, and all your servers, if you use on-premise infrastructure, they most likely have TPMs. And it's a discrete security chip on modern laptops and servers. It's a passive device, non-intrusive, so it's not that it hooks into like a memory of main CPU or something like and interacts with it like more expensive technologies. It's like it's a device, it does something if you ask it to do it, and if you don't ask, it won't do anything. But even with that, it's a foundation for modern platform integrity, authentication, and remote attestation. So even this small chip has all the primitives on which you can build like a cool feature like remote attestation, where you can remotely attest the integrity of hardware and software on the systems you manage. And as being a security chip, like its primary feature, it can handle cryptographic keys, which is really great. So this talk, like if you went to other TPM-based talks anywhere in the world, so when people usually mention TPM, they all talk about integrity and remote attestation, because this is where, like one of the best, this is why hardware vendors started putting TPMs in computers in the first place. But as a third-party application developer, people who develop software, like we have a lot of open source and commercial software, surprisingly, not much of it actually supports TPMs out of the box, right? So like, if TPM is so secure and so great, why can't I store like my SSH keys there? Why can't I store like my disk encryption keys there, right? And or like even like my third-party application, like some VPN or whatever, like or even a simple HTTPS server storing your private key inside the TPM, so it's better protected. So like not much software actually has out of the box support there. And the reason it would be great to use TPMs is like if you store keys inside the TPM, you will not be exposing them to your main application memory. So like keys may leak in different ways, and like who here remembers like Heartbleed? So why the key was leaked? Because the key was in the main process memory, right? So like, and if you don't have the key in the process, even if your process is buggy or you have an RCE or something like that, nobody can leak your key because it's not there. So, as an application developer, I want to utilize TPM for better security, right? If I'm developing an application, so I want something like that. My application uses this TPM, right? And is that easy, actually, right? So, as a user space application running on the operating system, I cannot interact with hardware directly. So, on Linux, I have to use a special dev TPM0 device to interface with the TPMs. But that's actually not it. Like TPMs are, as I mentioned, is a very cheap device, so it's like you can buy one for $5 or $6, so it's not very powerful, and generally TPMs do not support simultaneous like requests from multiple entities, from multiple applications. But modern operating systems are like multitasking, so you can have many applications trying to interface with a TPM, and TPM cannot handle that. So actually then to use the TPM as well, you need a thing called resource manager, which is an entity which kind of serializes access to the TPM from multiple operating system entities. So the TPM can process them in a sequential manner. But again, that's not it. Apart from this, I also need some kind of TPM library to interface with the resource manager, because resource managers have weird interfaces, right? And so here, the reality is like, for my application to use the TPM, I first need to learn the operating system interface, and I also need to bring it this purple third-party software as a dependency to my application to actually utilize the TPM. So let's zoom in on what is the resource manager. And the first iteration was actually a resource manager was a user space daemon. So it's a service that's running on your operating system and mediates access to the TPM, and you interact with it to talk to the TPM and ask it to do operation. And it is a little bit weird of a dependency from an application perspective, because it's a daemon. So now my ability to communicate with the TPM depends on some service running. And what if that service crashes, right? So like, it's not like I use a library, so my service crashes, but if it works, it works. Like some third-party application or service crashes, and I then cannot talk to the TPM, which people really don't like. So Linux developers recognize that fact, and they decided to integrate actually the resource manager into the Linux kernel itself. So with TPM 2.0, instead of talking to dev TPM 0, now you can talk to dev TPM RM, which stands for resource manager 0, which is an in-kernel resource manager, which does most of the resource manager functions inside the kernel. So now you don't have this extra service dependency in your stack. And if you can communicate with a device, you kind of like can communicate with the TPM, which is better. Now let's zoom in into this dependency, right? And here the situation is even worse. So like we have two major competing software stacks implementing this. So it's Intel TSS stack and IBM TSS stack. And the problem with these stacks, they have completely incompatible APIs. So, for example, you have to really decide beforehand which stacks are you going to use, and then you cannot, it's very hard to change this because you have to rewrite all your code to use a different stack. And we have different distributions out there, so if you want to write an application that works on every Linux distribution, some distributions may provide one stack or the other stack in their like package repositories and not two of them. So like if you want to write an application that kind of works across all Linux distributions, you have to support two stacks. So you have to actually write an abstraction layer on top of these two stacks. And but this is not only it. Also like some particular languages like Go, they don't even like external dependencies, so they have their own implementation, like from Google, Go TPM. I didn't actually look at the Rust ecosystem, but basically I assume either the development is ongoing or it's there already, because in Rust folks also use like Rust native thingy and not interfacing with stupid C. So like you have like many stacks to choose from and understand. This is a snapshot of a picture from the TPM software project. So this is like the TPM ecosystem project, and I mean, you see it has different layers, and you can use different like lower level APIs called TCTI, and higher level APIs called ESYS. So, and you have to understand the downsides and upsides of which. So, well, it's really, really confusing for an application developer who just wants, like, to do simple operations like a store, a key, and a TPM and use it, right? So, like, there is a lot of complexity going on. But even if you overcome all the complexity, you invest in all the research, understanding all of that ecosystem, it will still not work. Just because when you start interfacing a TPM from a user space application, most likely your user space application runs as a user or as your user or some kind of system user. And if you try to talk to the TPM, you get a permission denied. So this is like basically a snapshot from a default Debian installation. So by default, if nothing happens, the TPM device allows only root to talk to it. And similar with the in-kernel resource manager. So by default, the access is root only. So you can't expect your users of your application to run it as root. More confusingly, if you do install some TPM tools which install a TPM software stack, at least on Debian, so it will actually change the permissions on the TPM device, and it will create a new user and group TSS. So, and basically, you will be able to talk to the in-kernel resource manager if your user runs in the TSS group. But again, it is confusing for an application developer. How then I package my application? Do I just, even, for example, if my application uses Go TPM, do I have to just install the Intel TSS stack just to get permissions changed? And like, how do I, again, package my application that if I'm running as a normal user, like let's say I'm running an SSH client as a logged in user, right? So then how do I make sure my user is in the TSS group? So there is a lot of, application developers, again, don't use TPMs just because there is a lot of ifs they have to think about, and people installing their code, they don't expect that their code will work out of the box. Cool. This brings us to Linux kernel key retention service. I call it for short key rings or key store. Who actually knows that Linux had a key store? Cool. So Linux has a nice subsystem called Linux kernel key retention service. And so what it means is basically you have like a bunch of applications, right? You have the Linux kernel. And the Linux kernel actually provides 3 system calls like add key, keyctl, and request key. And applications can use these system calls to store cryptographic keys inside the kernel. So application can use the system call to provide some key to the kernel. And it was originally developed to provide keys to in-kernel crypto subsystems like disk encryption. So like because the encryption and decryption of data happens inside the kernel, but the kernel needs a key. There is a user space component, for example, crypt setup utility, which provides that key to the kernel. And the kernel now can transparently encrypt the disk. But later it was extended to that applications can also use that subsystem to operate on keys. So they can store these keys, they can retrieve them. And the nice thing about that, when you store a key inside the kernel, it becomes like a proper kernel object. So it has associated permissions. It has, it's subject to security module checks. So you can, basically, once you put the key in the kernel, you can design a very fine-grained security policy around it, which applications can access it and which can't. Internally, keys and key rings are broken into, key store is broken into keys and key rings. So you have the key rings object, and key ring objects can contain other key ring objects, or it can contain a key. So it's very similar to a file system hierarchy, except that the objects are in memory and inside the kernel. And the difference from files, for example, as you can see on the slide, a key can be simultaneously in several keyrings. And keyrings actually enforce the lifetime of a key. So if a key is not in any keyring, it gets automatically and securely destroyed from the kernel memory. Let's see a practical example. And by the way, all this was copied from a real terminal. So consider it as a demo, which never fails. So in this case, we have two users on the system, Alice and Bob, and as you can see that they don't share any shared credentials, so they're not part of the same group, anything, like totally separate users. And Alice, for example, wants to share a secret with Bob. So what Alice can do, Alice can add her secret to the kernel, and so her secret is key is hunter2. And yeah, and she gets back the serial number, which like every object inside the key store has a unique serial number. Now what Bob can do, Bob can create a new keyring and call it from others. So like this keyring, Bob expects other users to put secrets in so he can read it. And in order, this is where the permission check comes in. So by default, nobody can poke into other users' keyrings, but in this case, because Bob expects people to put secrets into this keyring, Bob sets permissions on this keyring that anyone can actually write to that keyring, but not actually read it. So like people could put keys in that keyring. And Bob somehow communicates the serial number of the keyring to Alice. And in this case, what Alice can do, Alice can move her secret from her keyring to Bob's keyring. And now we can see that Bob actually has access to the secret material, so Bob can read that secret or a password. And because Bob has the secret in Bob's possession now, and Alice actually doesn't. So Alice cannot read that secret anymore because the secret was moved to Bob. So simple, again, no shared groups, no shared credentials, like passing secrets around users. Clear so far? So keys in the keyring have several predefined types. So the example we just saw now is called a user key, which is the simplest type of key. And basically what it means is one process has some secret or a key. It can put it into the kernel keyring. And then either the same process or the other process which has appropriate permissions can read that key or secret back. Easy. The problem with this approach, it's simple, but it's not very useful, that because in this schema, right, the plain text secret material is exposed to the application process space. And again, we go back to Heartbleed and other types of attacks where secrets are harvested from the compromised process. There is also a slight modification of this key called logon key, and it's different in the way that a process can put a logon key into the kernel keyring, but it can never read it back. So it's not very useful for applications though, and the primary purpose of this key type is to actually support in kernel crypto subsystems. So when you open your encrypted drive on Linux, it's actually the crypt setup utility generates a disk unlock key, puts it in the kernel, deletes it from its process address space, and stays assigned the kernel, and no process can read it back, whatever permissions they have, because the key type itself does not allow it. So, but the kernel itself can access the key and decrypt your disk. There is also an asymmetric key type where, for example, and it currently only supports RSA keys, but if a process has an RSA key, it can put it inside the kernel, and either the same process or other process do not have to read the key back, but it can use the key handle and ask the kernel to perform cryptographic operations, like decrypting or signing with key. So this kind of like turns the kernel into a simple software HSM, where you can put RSA keys and then basically ask the kernel to do some operations with it. By the way, we have a blog post about this, and we have like an experimental OpenSSH patch, which replaces the SSH agent with this asymmetric key. So basically, you can put your SSH key into the kernel keyring, and then when you connect to hosts, instead of using an SSH agent, it will use the kernel to actually use that key and provide authentication via the SSH protocol. So it kind of has the same security guarantees as SSH agent, so you don't have the key in your SSH client memory address space, but you don't have to run this extra process called SSH agent to actually use the key, which is very handy. So this subsystem is actually would be really, really useful to integrate with TPMs, right? So it's kind of like software HSM. A TPM is kind of hardware device. It all feels similar. Like, what if they work together? And with limited support, they do. Remember that I mentioned that the primary goal of all the things, we don't want to expose plain text, secret, or key to the process address space. So there is a third key type which is supported and which uses a TPM called a trusted key. So what you can do is you can have a wrapped key, basically some secret encrypted with the TPM. And once you put it inside the kernel will automatically use your TPM to unwrap that secret. So the plaintext secret only exists in the kernel address space. But when you try to read it back, right, it will automatically wrap it again. So in user space, you can never get a plaintext cryptographic key, only the wrapped key. But up until recently, it wasn't very useful, right? Also, okay, so what? You can put a key inside the kernel, you can read it back, but you can't really use it, right? Because it's just wrapped and whatever. So the only use case for that was to provide a key for in-kernel subsystems like disk encryption. So to make it more useful, we can use the crypto API here. And this is what we did in Cloudflare and then submitted upstream. And just to clarify, Linux kernel key store and Linux crypto API, although sound similar, they're totally different subsystems, unfortunately. And in Linux kernel crypto API, you can actually use the kernel as a crypto library. And the way how you do that, you create a special socket type, which called the crypto socket. But it's not like a networking socket. That socket only connects your application to the kernel. And once you create that socket, the kernel internally will create an instance of some encryption algorithm that you request, for example, AES. Then you provide some secret or key, cryptographic key to the kernel. And then basically you can send the data to the socket and the kernel will encrypt it or decrypt it for it. So you can use, the kernel as a crypto library. The problem with this approach, so this key is not a kernel key, not a kernel key store key. It's just like a plain text key blob. And it has the same problems because if you want to use this subsystem, right, you still expose the plain text key material to user space. So we submitted a patch and it was actually accepted. So what if we combine the wrapped key schema and the Linux kernel crypto API subsystem? So in this case now, if you run a specific kernel version, for example, one process inputs a wrapped key into the kernel and the kernel in the plaintext key. And another process can create this crypto socket as before, but instead of providing the key directly, it can just reference an already existing key in the kernel key store. So by its serial number. So it says, instead of saying, hey kernel, here's the key for encryption, you say to the kernel, hey kernel, use the key by serial number X for encryption in this case. And so the kernel will actually instantiate it, and then you can encrypt and decrypt data with the key in the kernel key store, and without basically exposing the cryptographic material to user space application. Yeah, and as I mentioned, it's available from Linux 6.2. This is where the patch was accepted. The problem with this approach, again, that wrapped key is just an encrypted blob, so it only supports symmetric encryption, but not an asymmetric one. So you cannot like sign anything with this key. You can only do encryption or decryption. Actually, I wanted to add a signature support, but I realized that one of the kernel maintainers is actually working on it. So they have an experimental branch to add TPM-based key support, asymmetric key support into the kernel. Originally, they told me that they hope that this functionality will be available from 6.11 Linux, but as of this morning, I did check, so the Linux 6.11 is in RC release candidate stage, and there is no code yet, so it wasn't merged. But when it will be, the way how it would work, you have the similar system as a software RSA key, but instead of a software RSA key, you will have a key handle inside the kernel, and it will not the kernel will actually do the signature or decryption or signing, but it will just defer to the TPM to do this operation. Cool. Yeah, and like the key will be wrapped. But there is one problem with wrapped keys approach in general, right? And this is what we kind of encountered in Cloudflare. Let's zoom back and see how wrapped keys work. So like if you want to use a wrapped key, right? So you generate yourself a new key. Like I'm an application developer. I need an application specific key. So I generate a key. I wrap it with the TPM somehow. Right, and put in the kernel. But the problem is the kernel key store facility is it's in memory, it's stateless. So when somebody shuts down my computer or I do a server reboot, if I want to use that key again, I need to do some key management. I need to store it somewhere, right? So this brings state to the system. But this is not an ideal approach for Cloudflare because most of our infrastructure is stateless, and we consider our servers kind of like disposable. So I can take any server out of production, wipe it, and I expect it to work again when it reboots. So like, what if you have a diskless system? What if your disk abroading? What if you have an accidental wipe? So wrap keys are great that don't expose plain text cryptographic material to user space, but you still have to manage. You have to hold on to that blob. Otherwise, if you lose that blob, you cannot use your key anymore, which is not great. And on a server scale, it scales poorly. So basically, yes, you can have one application specific key to manage, but what if you have 5 or 6, or we have many services running in production, and they all require some kind of specific key. So it's all this extra state and extra key management that we have to manage. What if we take a different approach here? What if instead of wrapping a particular key to the TPM, we'll ask the TPM to generate it for us? So every TPM has a seed. And to be precise, the TPM has 4 seeds, but for the purposes of this presentation, consider it has only 1 seed. And it's seed unique to that device. And the TPM also has a KDF function, which is declared in the standard. So all this is part of the TPM. You can expect a TPM to have a seed and a KDF function. So what we can do here, we can actually provide some application-specific, and by the way, that seed can never be extracted from the TPM. But what we can do, we can provide application-specific info to that KDF function, and the KDF function will use the seed and our application-specific info to generate a unique key for us. And And it scales really well. So for example, you can have one key, but if you have many applications which are different, so they have different application-specific info, which is just, it's not secret, it's public, right? So you can generate many unique keys. But the nice thing about this architecture is all this state is fully disposable because the seed and the KDA function are fixed, so the whole process is totally reproducible. So for example, if I generate 1,000 keys, I can like throw them away, and on next boot I can regenerate the same keys again. So imagine, for example, you have a cheap router device, right? And you want it to have a static, but it's a diskless system, and you want it to have a static SSH key so you can trust it. So you can do that with this technology. So like even though you don't have any disk, if on each boot it will generate the same SSH private key from the TPM, you will see the same SSH key when you try to interact with this network device. It's worth mentioning the difference between, in the kernel key store, between the add key and request key system calls. So the difference is when you use the add key, you need to provide the cryptographic material directly to the kernel. It can be, depending on the key time, it can be a plain text key or a wrapped key, but you need to provide that data blob. So you provide, you call the add key, and the key gets instantiated. There is a different system call called request key, where instead of providing the key to the kernel, you can ask the kernel, hey, give me my key with this ID. And you just call that. And obviously, the kernel by itself, like every setup is different, and the kernel by itself doesn't know where to get your key from. So it can call a special user space helper, which is usually located at the path as being request key. And it will ask that process to actually create the key. But again, every setup is different, and to customize the behavior here, you can write simple plugins which satisfy different key requests. So like, and in this case, I made an experiment to actually write a plugin for this architecture and use a TPM to provide a unique application key for each application depending on some application metadata. Yeah, so in this case, my plugin will call the TPM to generate the key. It will return the key back to the plugin. The plugin will instantiate the key in request key, and then the key will go inside the kernel. The key will be instantiated inside the kernel, and the application will just receive an error code that everything worked, and the application can now use the key. So in this case, the nice thing about this architecture, like as you can see, the key is still kind of exposed to the user space, but only to that process, which is not connected to the network at all. And the application itself never touches a single byte of cryptographic material. So it's just as the kernel, give me my key, and it receives a handle, and that's it. And this simple plugin, I mean, it's a proof of concept, so sorry, it was hackily written in Python just to show that it works. You can find that link, and I can share the link later. So here is a simple demo. So first of all, if you download my module, you need to configure it so the request key user space helper will call it. So you do it like this. Don't worry too much about it. You can read about this configuration into the man page. So now let's see an example. So for example, I'm requesting a TPM2 derived key with ID test, and this is this is like the application metadata I wanted to use. So 32 path means I want a key of 32 byte size, and the path means I want the plugin to consider where my application is located in the file system for the uniqueness of the key. So if I generate the key and I generate a user key so I can read it back, if I read it back, I can see like some key, right? Now, let's delete this key right, and regenerate it. So you can see that the serial numbers here are different because that key was destroyed and this is a new key. But if you read it back, you can see, again, it's fully reproducible. So it has the same cryptographic material inside. So, moreover, just to prove that application metadata works here, so again, we can delete the key, but now we just move the requesting application to a different file system path. So I'm moving from user bin to my home directory. And if I rerun this with the same arguments, I can see that the key now is different. So this is like one way, let's say, to have a static SSH key here. If an application is a particular SSH path where the typical SSH daemon is located, it will always receive a unique SSH key, but no other application can actually generate the same key because it has a different application metadata. In this case, I can also show that your requesting user is also considered. So if I rerun the same application but with a different user, like as root, I will still receive a different key. So even though like I can run an executable on the same path from different users will receive different keys. So I cannot steal an SSH key because SSH daemon usually runs its root. Me as a user, I can run the SSH daemon executable directly, but I will get a different key in this case. So I cannot steal the root's SSH key. There is a second mode in my module called, instead of the path, I call it checksum. So it's basically an integrity hash of the requesting application. And if you use that, so you can generate the key again. You will get some bytes. But now I'm copying the keyctl utility to a different path, right? And I rerun it again, and I still get the same key. So now it doesn't matter where my application is, but my key is specific to the code running in this application. So like, I can put an application wherever I want, but specific to that executable, I will always get a unique reproducible key. And to show that it works, I'm actually now patching the keyctl utility. So I know it has an error string called bad message, so I change it to bad massage. I change 1 byte, right? And so the tool will still work because it's just an error string, but if I rerun it, you can see I'm already getting a totally different key because my integrity of my application was broken, so it's a different application now, different code, so it gets a different key. And similarly, you can also do like asymmetric keys as well. So, for example, you can generate some test data. I will not print. You can't really read the asymmetric keys. You can only use them from the kernel key store. So if you generate an asymmetric key, you can sign some test data. Then we can delete that key, and we can regenerate it again, sign the same data, and because we use RSA PKCS1 signature, we get the same signature. So basically then the key is the same. Yeah, and as I mentioned, the only drawback of that approach is, even it's a slight drawback, right? So I still have this plain text key in the user space, even though it's constrained to that particular process. What if we do it directly in the kernel, right? So this would be a better approach. So you can actually request the key from the kernel, and it will use basically the same algorithms to generate you with application-specific keys. And this is where I want to go. So I actually created a patch set for consideration for upstream, which implements all of that inside the kernel with no extra support. The only problem with V1 of this patch set that one of the feedback was I don't believe that this will ever be a solution for any problem that exists on the planet. So I don't know, like, this is why I'm also presenting this problem here. Do you think it is useful? And if you manage like a fleet of IoT devices, for example, will it help you to better manage cryptographic keys? Well, this is basically all I wanted to present today, and the conclusions are that interfacing with TPMs are hard, so that's why most applications avoid them altogether. The Linux kernel key retention service can be a good layer to abstract the TPM complexity for applications, but some additional development is needed. But the upside is, like, any application can use key store system calls. So this is where you will never have problems with dependencies or like incorrect permissions on TPM device, because you're just interfacing with the kernel, and kernel will talk to the TPM on your behalf. And I think like TPM derived keys is a good alternative to existing TPM wrap keys, and it provides you with similar hardware-backed security, but with potentially easier key management. And you can easily use it today if you can actually do it via the request key plugin I presented earlier on the current kernels, but if I manage to push my idea through the upstream, and probably in future kernels you don't need any extra software plugins to actually make it work. And exposing TPMs through Linux kernel key store is better, so it's already somewhat exposed, but better. Can provide with a straightforward path to adopting hardware-based security without too much exposure to TPM and kernels. And it's probably true for other security chips, like other architectures like ARM have different things, and they also should be exposed through Linux kernel key store, I think. So any application out there can just use it. Yeah, here are some useful links, which you'll probably get if we share the presentation. So the first two links are to surprisingly good kernel documentation about the Linux kernel key store. The third link is to the patch set that I mentioned from upstream maintainers that will bring support of TPMs to asymmetric wrap keys. You can follow that thread to actually understand when it's actually merged, and so you can start using it. The fourth link is linked to the code of my POC for the request key TPM derived keys, and the fifth link is linked to my patch set proposal to upstream to add derived key support directly into the kernel. Thank you very much, and I think we have time for questions.
All right. Thank you again, Ignat. Can we give him a round of applause? So appreciate. Okay. Any questions from anyone, please?
Hi, thank you for your talk. Do I need to run each application under a different user ID to make sure that they can't access each other key material in the kernel?
So in the V2 iteration of my patches that I'm cooking, I want to add, there are pros and cons of this approach, whether you should consider the running user ID to generate a unique key, because there are different needs. So for better security, for example, you want to consider it, because if other user runs your executable, they can extract your key basically, right? But there are use cases and setups where it's not preferable. For example, let's say if we need a static key from an application, regardless of which user it runs, there are use cases for that. So in my next iteration, I wanted to make it configurable. So as a requester of the service, you actually tell the kernel which specific application metadata to consider. So you can say, I want to consider like the path, the user ID, and the checksum. Or you can select any combination of these, and then basically you will get the key depending with properties depending on what you requested. Does that make sense?
Can other applications spoof that application metadata that goes into the key generation? Can the information be spoofed or faked in some way?
Well, it depends on the metadata, right? So I don't see how they can spoof the user ID, for example, because basically the user ID used by the kernel key store for all the permission checks in the first place. So I assume that that path is more or less secure, right? I can see where an application may be able to spoof the path. Probably not, and depends on the implementation, maybe even a checksum. So with the user space approach, the checksum potentially could be spoofed. For the in-kernel approach, my approach was to hook into Linux integrity measurement architecture for the checksum. So like you don't checksum the application yourself. You just ask the subsystem which is responsible for it to do it for you, and it does it in a secure manner. So in that case, it will not be possible to spoof the checksum.
Thank you.
Yeah, I just had a question. Is there a minimum TPM version that's required for this?
2.0.
Okay.
Yeah. So like I never mentioned, like, and TPM resource manager device in kernel is not even available for 1.2, and like 1.2 is considered insecure. So if you have an older laptop with 1.2, it doesnn't apply to you. Just forget about it. Or buy yourself a new TPM and plug it in. It's not that expensive, actually. Any more? Going once? Going twice? Thank you.
Okay, thanks again, Ignat, for your time.